actually stability means physically? For example, if your system is not stable, what could happen? Like, it can damage your system, all right? Or maybe, depending on the nature of your system that you want to control, like, it can damage your surrounding, and it can even damage human life too, all right? So it is very important for stability to be there once you start controlling or operating your systems. Okay. From the time response plot, if you just consider response plot, if your plot is growing, the output, plot is growing, so that means that for the time plot for that, if it is decaying or it is coming down to the final value, all right, so in that means your system is marginally stable, all right. How actually you can determine the system is stable? That's the most important thing. Okay. After defining the stability, what stability is, why is it important? Okay. Now, like, how actually can you determine whether your system is stable or not? Because we want to have a mathematical tool or mathematical handle that, so that we can determine if our system that we are, doing analysis or we are designing actually, whether it is stable or not. Okay. All right. So, if you have a closed loop system, and if your poles are lying on the left half plane, all right, what does it means? That you have the negative value for your real part. Okay, so your system is stable. Like, if the poles of your system, they are lying on the left half plane, they are stable. Same like, in your DSP, you may have considered the unit circle. Okay, and your Z transform is there. So you might have said that if the poles are lying within the circle, okay, they may be stable. If outside, they are unstable. All right. Similarly, in the continuous systems, the transfer functions that we have considered, okay, if your poles are lying on the left half plane, it means your system is stable. All right. But if any of the poles, like, if it is lying on the right half plane of your right half plane, then the total system would be unstable. Okay, because of that particular pole. Okay. Similarly, if your poles are not on the right half plane, but they are lying on the y-axis or JW axis, as we know that in the S plane. All right, we have the sigma axis or real value axis on the on the horizontal line, and the vertical line we call it the JW axis. Okay, or imaginary axis. So if your pole is lying there, or if your poles are lying actually there, uh, or maybe on the left half plane, combination of both two, then your system would be marginally stable only if it's the multiplicity of one. Like, if the only if you have a pole, let's say J2 plus J2 and minus J2, but if you have only having that, then it means your system or your system is marginally stable. All right. But if you have multiple poles at J2 plus J2 and minus J2, then it means your system is unstable. All right. All right. So next, moving forward, probably, this may further explain you. So, for example, you have this system, the closed loop system or feedback system. You just solve for it and you get the poles here. All right, in the upper here. So you have one pole down here at minus 2.672. That's a real pole. Then you have a pair of complex conjugate poles. They are lying around at minus 0.164 plus J 1.047 and minus 0.164 minus J 1.047. So now in this case, like, your poles are lying on the left half plane. You don't find any poles on the right half plane, or you don't find any pole on JW axis. Okay. So in such a case, like, when you plot it, like, it's under that case, for example, in second order system. So you will see that, system has one response, then it settled down to the final value of 1 as it plotted here. Your system is control system, right? Or your system is stable actually. All right, in this case. Now consider another case, like, here down here. Once you solve for it, you find the closed loop transfer function for that, and you look for the poles of the system. by looking at the polynomial of the denominator. You get one pole at minus 3.087, another pole's complex pair, conjugate pair at somewhere around J 1.505 plus minus some real values there too. But you see that there's one pole which is on the right half plane, right side of the plane, okay? And this is at 0.0434, all right? You see over here. So what does it mean? Like, one of the poles is on the right half plane. As by definition, if your pole is lying on the right half plane, okay, your system would be unstable. Now you see the response. If you plot for it, you see that the system response is not converging at the value 1, like it happened in the upper case, all right, but like its value is increasing, it's growing and growing, okay. So what does it mean? That your system is unstable, all right. If you keep on this system, that it will damage your system ultimately, all right. Let me just okay, there's one small topic there too, which tells us about, like, um, even without solving for the poles, if you just see the polynomial or on the imaginary axis, and so by looking at the poles, then we are able to tell about the system. All right. Now, like, there's another thing, you can actually kind of estimate, not exactly, but like somehow uh, about the stability of the system by just looking at the polynomial of the denominator, okay, without solving for the uh, poles actually. So how there's some, actually it's not completely there, but like you can get some hints there whether your system would be stable or unstable or maybe marginally stable, um, just by looking at the denominator of the polynomial or the transfer function that you are having, okay. For example, under certain condition, we can draw the conclusion that a system would be, there's sufficient condition, a system would be unstable if the signs of the coefficient of the denominator of the closed loop transfer function are not same. What does it mean? If you have the polynomial of your um, of the denominator in your closed loop transfer function, if you just look at it, so the denominator maybe, let's say, is s4 s5 s5 plus s4 plus 3 s2 or plus 5 7 s1 or plus 5, whatever is the denominator. But if there are, let's say, positive signs with the coefficients, okay, if you just look at the denominator, but if there is maybe one, or two of them are negative, if any of the coefficients of the denominator is negative, which will give you an indication that the system is unstable. If you find, just look at the denominator of the closed loop transfer function, and if you see any negative sign over there, which means that your system would be unstable even without solving the for the roots of your, or for the poles of your system, okay. Similarly, if any power of s is missing, what does it mean? Like, for example, if your pole is there at s4 s3, um, so s4 plus 3s square plus, let's say, the s term is missing, okay, plus just is 7 or 5, whatever it is, okay. If any of the power of s is missing, it means your system is either unstable or marginally stable. So what does it mean? That if any power is missing, it is a short uh, indication that your system would not be stable, all right. It may be unstable or maybe at most a marginally stable system, okay. But if if you have the systems, the third thing is that if all the all the coefficients of the denominator are positive and none of the values or none of the powers of s are actually missing, so then we don't know about system, or maybe it's stable, unstable, or marginally stable. But if there are two things actually. If any of the coefficients of the system denominator, closed loop transfer function denominator, is negative, it means your system is definitely unstable, okay. If any of the power is missing, it means of s is missing, it means your system is not stable. It is maybe unstable or maybe marginally stable, okay. But if all the values are positive and all the uh, powers of s are there, they are not missing any, so it means it could be any case, stable, unstable, or marginally stable. You can determine from the polynomial.